All right, so today we're going to actually start chapter two, which is our first look at derivatives, which I think I've mentioned before. This is easily one of the most important concepts in all of calculus, if not the most important. So we're going to see what definition we're going to use based on limits, and then we're going to learn some rules that will make it a lot simpler. All right, so we start out by taking a look at the so-called tangent line problem. And what they're going to have us do here is take a look at this graph. Let's copy this into the notes. Now, I do want to remind you that if you were to draw a line through a function that crosses twice, let's say we have something like this. Here's our function. A line that cuts through this curve at two different points is referred to as a secant line. Of course, if we instead touch the function at exactly one point, then it becomes known as a tangent line. All right, so just as a quick reminder, that's a secant line again means that it cuts to the curve twice, and a tangent line touches it exactly once. So what they're doing here is defining, in the most formal possible terms, the slope of a secant line. So they're assuming that we start at point C, which is some constant, and then over here we have C plus delta x, which is a constant, although a very small one. And then the corresponding values of y would be, of course, f of c and f of c plus delta x. So to calculate the slope, which in this book will be written as m with a little secant here, we know that it's delta y over delta x, but here, the way it's written, we're going to write it as f of x, c plus delta x minus f of c, which is the vertical distance between these 2 points, all divided by delta x, which is, of course, the distance between these 2 points. Now, what are we going to do with this information? Well, it turns out, and yeah, and by the way, they're showing us that there's different ways of actually expressing the same information. The slope of the secant line, f of c plus delta x minus f of c over delta x is what we're looking for. Now, what we're going to do, and this graph is meant to indicate that what we're trying to do here is this. Imagine again, you've got a secant line, and let's say here's our tangent line to the same function. Now these graphs are not perfect, but you can see what I'm doing. What they're trying to show you here in those many graphs that they had here is that if the 2 points here continue to get closer and closer to each other. Let's say, for example, we take the same function and try the points. Let's say this is some other x, and this is the new x plus delta, or this could be the same x, but now this is a different delta x. Uh, yeah. So, in other words, what we're getting at, all the purpose of everything that's about to happen is this. As the two endpoints get closer to each other, which is the same thing as saying delta x is shrinking, the slope of the secant line gets progressively closer to the slope of the tangent line. Okay. So in other words, as we keep moving the 2 points closer together, the slopes of the tangent line and the secant line, eventually they'll be the same. All right. So with all that being said, what we're going to do is take this expression and we're going to do something very interesting with it. We're going to take the limit as delta x approaches zero. Okay. So in other words, now of course we now know what limits mean, how they work. We're getting as we get closer to one variable, we want to know what happens to another variable. So here we're taking the limit as delta x goes to zero of the slope. This is the slope of our secant line. And of course, so is this. These are just two different ways of expressing the same thing. Okay. So now what we're going to do to find the slope of this secant line, which will equal the slope of the tangent line when we take the limit, we're going to take the limit of this expression as delta x goes to zero. Okay. Now, by the way, I've noticed with this book, when they want you to use the secant, the slope of the secant, they read it like this. If they leave out the subscript altogether, they usually mean the slope of the tangent line. And that's the case here. All right. So, you got to get used to the book's notation, but that's what they're doing. All right. So now, in order to do this, we're going to need an example. All right. It doesn't make any sense. I mean, it's fine that we know this definition, but we have to use an example. Otherwise, it'll be very difficult to understand what it's telling us. So here's the example they dreamed up. F of x equals 2x minus 3. And what they want to know is what is the slope of the tangent line to this function at the point 2. Now, of course, this is a linear function. Looks something like this. And when c equals 2, the function has a value of 2 times 2 minus 3, 4 minus 3, which is 1. Okay, so what we're going to do now is apply this expression to this specific case. All right, so we already know f of x is 2x minus 3, and we know that c is equal to 2, which means that f of 2, or actually I should write it like this, f of c is equal to f of 2, which in turn, as we've already seen, is equal to 1. But what about this one? C plus delta x. Okay. So that's the same thing as 2 plus delta x because we've already decided that c will equal 2. So how do we figure that one out? Well, we take our original function and we replace all the x's with 2 plus delta x. And now we can solve for this algebraically. And we end up, whoops, sorry, that's 2. Ultimately, we end up with 1 plus 2 delta x. Now, that means we have everything we need to plug into this expression. So let's do it. And let's see what happens. So we're taking the limit of delta x as it goes to 0. F of c plus delta x, as we've just seen, is 1 plus 2 delta x. F of c is 1. We've already shown that. Now these ones drop out. We're left with 2 delta x over x. And so we're taking the limit now of a constant, and we've already seen that the limit of a constant simply equals the constant. So the correct answer is 2. Now, what that means is that the slope of f of x at c equals 2 is 2. Okay. Now, we already knew that because this is a straight line. And that means that the slope is a constant. And of course, it's equal to 2. So if I were to try to describe a tangent line here, well, it would just be touching at that exact point, and the two would have the same slope. It would look something like this. Well, all right, they'd both be exactly the same shape. All right, so in other words, this is a very simple example, but it demonstrates that we can solve for the tangent, the slope at least of the tangent, at any point by using this approach. It's not necessary in many cases, but this is how it's done. Okay, so in other words, it's a very formal definition, and you'll probably only need to do it maybe once with your WebAssign problems. And after that, you can just use the rules that we're going to see later on. Okay. By the way, once in a while, you run into a very strange case. Like here, if you notice, the tangent line to this curve is actually a vertical line which has an undefined slope. And so this is something that could happen in principle, but it's very unusual. But they just want to mention that right here. Now, after all that discussion, we finally get to find out what this mysterious derivative is all about. Okay, so you'll see that it's being defined in terms of limits. Now, here, we have a more general expression. We don't have a constant c. Instead, we use x. Sorry, not definition of a limit, definition of a derivative. Now, I do want to point out there are several different notations that represent the derivative of a function. This is one of them. We pronounce it in English f prime of x. Now, in the slides, they'll show you there's several other alternative approaches to doing this. Let me just go grab that for you. It's a lot. Look at them all. There's at least 5 Luckily for us, there's only two of them basically, maybe three that we'll use on a regular basis. Okay, so here's our f prime of x. We also have dy dx, y prime, and all the rest. So hands down, these are the most commonly used ones, but we'll also use this one once in a while too. How does this happen, by the way? It's because, math evolves over the centuries. It's contributed to by many different authors. They all use slightly different notation, and this is what ends up happening. So we just have to get used to it. Okay, so what we're going to do is an example. Uh, Now, by the way, there's an example in the slides, but it's such a mess that I think I'm going to substitute my own example right here. You can go look at it later on, but it just sometimes they'll start out a new concept with a horribly complicated example, and I think that's a terrible mistake. Okay, so how does this work? All right, let's go back and revisit our definition. Okay, so f of x, we already have it. F of x plus delta x, what does that equal to? So again, just like before, you go to your f of x and all the x's become x plus delta x. So you notice what I've done here with x squared, it became x plus delta x squared. And this one just became 2x plus delta x. Okay, now when you square x plus delta x, you're just multiplying x plus delta x times itself. And this we can actually do with FOIL. So we may as well take advantage of that. F is here. O is these two. It's just called x delta x. And this one is the same, actually. Even though it's written in a slightly different order, it's x delta x. And then here last would be delta x squared. So when I bring this together, I get x squared plus 2x delta x plus delta x squared. Now that goes into this formula. This takes the place of f of x plus delta x. So let's copy this one more time. And so this becomes, all right, so once again, this was x squared plus 2x plus delta x squared. Now, here's the thing though, don't forget the original function is actually 2x squared plus 2x plus 3. So we only have this piece. Oh, actually, in fact, we have to be extremely careful here because all of this has to be multiplied by 2. What you're seeing here is just x plus delta x squared, but we have a 2 here as well. So let's write that down here. And then we have 2x plus delta x. And then we have a 3. And now I'm running out of space. What you see here is just this piece. We still need to subtract f of x. So let's do that. So then I'm going to, in the down here, let's write this down here. Minus, now remember, f of x, the original function was 2x squared plus 2x plus 3. And then we still have to divide everything by delta x. All right. So, you know what, this is still kind of messy. I was hoping to get a simpler example, but I guess it didn't happen. So we're going to have, so let's first was distribute this true across all these terms. Now here I'm going to add this 2x plus delta x. You have to distribute that too. And then over here, you still have this 3. And then we have to subtract these terms. Let's do it like this. And then we have to divide everything by delta x. Now, fortunately, there should be a lot of cancellations though. And they would be here and here, here and here, and then here and here. So we're left with x delta x plus 2 delta x squared plus 2 delta x. And then there's going to be a lot of cancellation here too. Each of these has a delta x in it. So we have 4x plus 2 delta x plus 2. But now remember, delta x is approaching 0. So we're going to substitute, as we did so many times in chapter 1, um, delta x equals 0. And so we end up with 4x plus 2. Wow, that was an ordeal. Now, what exactly does it represent? This is the slope of the tangent line to this function, which in turn means this is the derivative of f of x, which means I can write it like this. For f of x equals 2x squared plus 2x plus 3, f prime of x is 4x plus 2. Wow. So in other words, whatever this function looks like, the tangent line has a slope of 4x plus 2. We can use, if we're looking for a specific point on the original function, we can substitute and find it at that point. But basically, this is the formula that we'll use to solve for the tangent line slope at any point on this curve. Now, you'll be relieved to hear that we don't normally take derivatives this way. This is the hardest way to do it because we're following the definition. In general, we'll be learning a bunch of rules that will make all of this completely unnecessary. You'll be happy to hear. Okay. But you do need to see this once. What is a derivative? This is how it's formally defined. After that, you can use all the rules you want. Okay, good. I can hear the cheering through the screen. Now, if you want to tackle this example, it is really a nightmare. It's just so messy. I think it just obscures, what we're trying to learn here, but you can go ahead and try it if you want. Um, Differentiability and continuity, the derivative um, is equal to this. By the way, let's grab this graph. So what we're seeing here is a function, whatever it is. And just like before, what we're interested in now is the slope of this tangent at this point. And what you're seeing here would be the slope of this tangent line is the derivative evaluated at C. Okay. So how do we find it? Hold on. Now, because the derivative itself is actually a limit, just like in the other chapter, it must be true that the limit approaching from the left and the right are equal to each other, and they have to exist as well. So if you go back here, the limit as we approach C from the left of f of x minus f of c over c on this side, approaching from the right, they'd better equal each other. Otherwise, we have a problem. It would mean that the derivative does not exist at that point. Okay. At point C. Okay. So formally, f is differentiable on a closed interval when it is differentiable on the open interval and the derivative from the right at A and the left at B both exist. Yeah, we're going to skip over that one. So now here's one of those cases where there isn't a derivative at this point, x equals 2. It's a very strange case because what's happening is that the slope, as we get closer and closer here, the limit um, is I'm sorry, it's not, no, sorry. The derivative from the left-hand side, remember the derivative is the slope. And over here, it would be positive 1. So in other words, they're different. And as they approach this point, you can see there's a break, a sharp break in the curve. It's not a gap, but it's not smooth and continuous like something like this would be. So when you see like sort of a sharp point in a graph, that means that the derivative does not exist at x equals 2. But the derivative on this side is 1, as you just see here. And on the left-hand side, it's -1. But when we get to exactly this point, then it no longer exists because the two of them are coming from different values. And so here you can see the slope of this curve is very close on either side of the point. But here it's not. So what you're seeing here is an exception. It's a strange case. You don't see these all the time, but that means that there's no derivative there. And if there's a discontinuity, we're going to have the same problem. And I'm sure they'll get to that in a few minutes. Um, yeah. So in other words, this is just what I was saying. It's the derivatives are different, but the limits, as you can see from the left, is -1, which remember the limit and in the slope of the tangent line is the same. And on this side of the fence, it's +1. And since they're different, that means the derivative does not exist at that point. All right, let me write it down here where there's more room. And so they're not equal to each other. And therefore the limit can, well, of course, the limit, as we saw in a previous chapter, does not exist, which means that f prime of x at x equals 2 also does not exist. All right. So again, this is all very theoretical. Don't you worry. Soon enough, we'll start learning the rules and you'll see that it's much, much more down to earth. Right now, it seems like, ooh, this is harsh. Now, what is differentiability? The ability to take the derivative of a function is called differentiability. The fact that a function is continuous is simply called continuity. Those are adjectives. So being differentiable implies continuity. So I think we started to use this notation the other day. Um, so this little arrow, you see this all the time in math books. It's meant to represent the word implies. It's another way of saying if the first statement is true, then the second one is true automatically. But because it only goes one way, um, It doesn't go the other way. In other words, f is continuous. Oops, at x equals c does not guarantee that f is differentiable. It's not x, f. Okay, so you got to be careful with these logical statements. You're going to see them all the time in calculus. So this one is saying being differentiable guarantees that it's continuous, but being continuous doesn't necessarily guarantee that it's differentiable. All right, so I think what they want us to do is use that same approach to find the tangent to the graph of the function here at this particular point. It doesn't say that, but I mean, that's the only technique we know right now, so I guess we better use it. Oh, yeah, I'm always scared that I'm going to this handwriting works fine, but it's easy to mess it up. One wrong step and it all gets jumbled together and you'll never get it apart. It's like spaghetti that's not cooked properly. All right, it looks good. Was it 9? Um, 9 minus x squared. So remember the definition. I've got it up here somewhere. They just felt like, they changed it to g of x, but of course that doesn't matter. Yeah, sometimes it can get really stubborn and it won't let me copy. Oh, there we go. Yeah, all right. No, I'm just double checking to make sure everything looks normal. All right, here we go. Now they're also specifically asking us for the point 4 comma negative 7. Oops. See, it's so automatic that I use F. I have to be careful here. All right. So now we already know what g of x is. That's 9 minus x squared. What do we do about that g of x plus delta x? All right. Now, again, we had this earlier, but let's run through it one more time. You can figure this one out with FOIL. And let's do that right now. F O I. Last is over here, L. And now, of course, remember, I'm subtracting that from 9. We have to be very careful with this. And of course, we still need to subtract from g of x. Okay, so we know g of x plus delta x is this. G of x was 9 minus x squared. And then, of course, we do not want to forget to divide by delta x. Now we can simplify it, and we should get some cancellation. All right, so we have two, these drop out, these drop out. Then we draw, now of course there's more cancellation here because everything is a function of delta x. We'll have minus 2x minus delta x. And now, of course, because we're taking the limit as delta x goes to 0, this goes to 0, and we ultimately end up with minus 2x. But because they're specifically after the point for negative 7, okay, so the original function is going to be a parabola, and the point that we're after 4 would be maybe here. Oh, that can't be right because it's negative 7. Hmm. Oh, I see what they want us to do. They just want us to substitute X in here. Negative 8. That's what they're after, and that would be C. All right. Oh, another one. Okay. Well, at least we'll get some good practice here. All right, so let's go grab the definition. Oh, I see what I did. Okay. Okay, so what we have to do is solve for f of x plus delta x. All right. Now, we already saw earlier that when we square this, it became x squared plus 2x delta x. Delta x squared. Whoops, no. We'll drop the parentheses in the next step. All right, now hopefully we can simplify this thing. Well, maybe not. No, actually, this is fine. F of x was 3x squared, negative 3x squared, plus 6x minus 8. So the numerator of this expression is, well, it's going to be a tight squeeze, let me tell you. Oh, I just barely made it. Now I'm going to, now over here, keep in mind, I've got a negative, so I have to be careful. So that makes this positive 3x squared minus 6x plus 8. Now, ideally, there'll be some cancellation. Oh, yes, there is. Okay, wonderful. And of course, now there's a delta x in each of those terms, so it becomes Ooh, what just happened? Okay. So we'll have minus 6x minus 3 delta x plus 6. And of course, this goes to 0. So we end up ultimately with minus 6x plus 6. Let's see if that's all they wanted. Yeah, that's it. So it's A. Wow. Oh my God. All right. Now that was 2.1. I'm not sure if we have time to do any more, but let's see at least what's in 2.2. Ah, it looks like it never got that open. Ah, the rules. Yes, the rules. You'll be so happy when you see how straightforward these rules are. So, what this is all about in 2.2 is the rules that we'll follow. We're not going to do these limit definitions maybe ever again. And I don't think anyone's sorry to hear that. So, we'll start with the constant rule. By the way, if you notice, they're switching the notation to dy dx. So remember, f prime of x and dy dx both represent the derivative of a function. So, don't be put off by that. It's just, it's the same thing. So, for example, here they're writing it as d, and instead of putting the y up here, they're replacing it with the constant. Okay. Now, here's why this is happening. Remember, the derivative is actually the rate of change of one variable with respect to a change in another variable. A constant doesn't change. So therefore, it must have a derivative of 0. Okay, and that's all there is to it. So when you see a constant, just 0. Nice. And of course, well, and you know what they've decided to do here? They're changing the notation on us. Sometimes it's dy dx they have in here, f prime of x. Then they even change the letters, s prime of t. They all mean the same thing. Okay, now I'm not sure what they're doing here. Well, I guess they're building up to this. Now, this is really maybe the most important of all the rules, the so-called power rule. And the way it works is this. Now, n is a constant. It often it's an integer, but it doesn't have to be, and it also doesn't have to be positive. The derivative is equal to n times x raised to the n minus 1 power. Oh my God, it could not be more important. But as you can see, it's a very straightforward rule. And so here's some quick examples. So here clearly n is 3. So we end up with, and again, you can write it as f prime of x if you want, or dy dx. It's the same thing. 3x to the second power because it's 3 minus 1. Okay. Or if you want to do it more formally, keep in mind there's an implied 1 here. But of course, it's just 3x squared, any way you look at it. G of x equals the cube root of x. Now here, the trick is to rewrite it. That's right. Remember, the cube root of x is x to the 1/3 power. So therefore, we can use the power rule where n is 1/3. And of course, when you subtract 1 from 1/3, you get negative 2/3. Interesting. And how about this one? 1 over x squared. And so what they're going to do is have us rewrite this as x to the minus 2 power. Oh, that's right. Okay, so when you subtract 1 from negative 2, of course, it becomes negative 3. How do you like that? Or if you prefer, you can write it like this. Same thing up here. You could rewrite, oh, sorry. This one up here could be rewritten as, well, this would be kind of awkward, but this would also be correct. Okay. All right. So now what'll happen sometimes here is that they're calling it the constant multiple rule. If you notice what's different this time, it's not x that we're taking the derivative of. It's just some function f of x with a c. C is a constant. So like the c basically just stays at c. No matter what happens to f of x, when you take its derivative, you still end up with just c f prime of x. So as an example, here we go. They've got quite a few examples. Y equals 5x cubed. C is 5. N is 3. So we're basically doing two things at once. We're in fact essentially holding this 5 out here and then applying the power rule. And that's our final result. Okay. So again, after you've done a few of these, you'll start to realize pretty quickly that a lot of these are just not very difficult. It just takes a little practice. What do we have here? 2 over x, which I recommend you rewrite as 2x to the minus 1. So that now you have a constant and you have the power rule. And that leaves us with minus 2x to the minus 2, or minus 2 over x squared. And then what about this one? F of t said I'd like to change the letter sometimes. 4t squared over 5. So 4/5, of course, is a constant, and we can apply the power rule, and the constant stays outside. Now, of course, t to the first is just t, so we'll just leave it like this. Okay. Now, it's going to get much more complicated very quickly. Um, oh, wait a minute. Well, they got a few more. All right, I'll tell you what. It's getting late. Why don't we save the rest of these for our next session, and we can dive into the more complicated rules as well. These are fine as far as they go, but you'll see it gets quite messy when we start multiplying and dividing functions. So I think this is a good place to stop. So hopefully you've got a good feel for what derivatives are and how they're defined and how to calculate them. So this is going to be a very complicated chapter. But when we're done, this is like the foundation for everything that follows. So this is where it really gets really important. Okay, serious. This is serious stuff. So we'll see you all next time.